You can start.
Okay.
Oh, yeah.
Oh, it did. Oh,
Thank you.
sorry.
Cool. Awesome. Well, good afternoon and welcome. We are Team Major Props here to present our critical design review. My name is Kevin Burke. I'm the team captain.
Sorry. There we go. I'm Michael Pioro. I'm the meeting coordinator, also the strain gauge lead.
I'm Connor DiFrancesco. I'm the document manager as well as the controls lead.
I'm Thomas Napi, the secretary and optical and accelerometer lead. So as before, we still have the same problem statement. We're building a propeller test stand to be mounted in a wind tunnel for the aerospace department. Along with that, we still have the same stakeholders as before. Dr. Z, Dr. Jemmy, the capstone teams, College of Engineering, aerospace department, as well as future students. Since the last one, we've defined or sort of narrowed down our project needs to our three major ones. It must be robust, user-friendly, and inexpensive. These are the three main concerns with the current test stand that they have. And so those are our three kind of primary needs. We still need to collect the same data and get that to the embedded system with the thrust, torque, speed, voltage, and current. We still need to control a motor and collect all that data to a computer with the time. On our requirements table, we made one change. That being PC communication via USB. We removed costs from that because that's more of a constraint than a requirement. And so we replaced that with our PC communication because that is one of our defined requirements. And to address our new finalized design, Connor is going to take over.
Thank you, Thomas. So for our conceptualized design, after taking into account the needs of our stakeholders as well as the requirements that we established, we ended up coming up with the four designs that we presented in the PDR. After going through the Pew Matrix design, or the Pew Matrix, as well as talking to Ross, as well as realizing that the time restraints are going to be our biggest restraining factor, we decided to go with what we were calling the bare bones system. And the bare bones system essentially has every component separated, allowing us to quickly swap out components in the event that we need to during both the development phase as well as the post-development phase. That way, if something that we ended up with the final result, if something needs to be changed in the future, it can be changed with relative ease. So the way that this design works is, as you can see in the top, it's sectioned off mainly as what each sensor is measuring. So on the top would be the torque, thrust, RPM, as well as the vibration sensor. And those sensors will be communicating with the microcontroller development board, and then sending that out to the PC for recording data. Now, this is a very broad overview of what our conceptual design, and we're going to be going into more specifics during this presentation. Specifically, the complete embedded schematic that we've designed. So this system schematic This system schematic is nearly complete with containing almost everything that will be in the final design. The best way to observe this schematic is to break it down into its four main categories. That being the ESP32 system, the sensor system, the power system, as well as the control system. Throughout this presentation, we're going to break down each system individually, starting with the brains of the operation, the ESP32 system, which Michael will take over.
So for the ESP32 system, we decided to go with the ESP32 Dev Kit C. This board will act as the brains of the entire system, allowing for inputs from different components and sensors, outputs of PWM signals to various components, and also data transfer and communication to and from the PC. So the team ended up going with this microcontroller board because of the features that it provides, starting with 34 GPIO pins. Those will allow connections as simultaneously to multiple components and sensors. And it also has two I2C pins if we needed to expand on that capability a bit further. The board also has a 5-volt power supply capability. So, or 5-volt power capability. So it can be powered off of a 5-volt power supply. So as it stands right now, we're powering everything off of the PC connection with the USB, just the 3.3 volts. But we wanted to try to separate the actual serial communication with the PC and the power, so that if anything were to happen with the PC, the board would still be powered. And so, yeah, and we would just keep the USB interface for just communicating to and from the PC. All of the pins have PWM capabilities, so when we're working with the ESC or any other components that need PWM, we'll have that on hand. And then finally, the board will be programmed using the Arduino software through the Arduino IDE, which will allow us to build the software a bit better, because there's multiple different data libraries, and really allow us to formulate this entire sensor system that we're trying to integrate. So first off, with the sensor system, we decided to bring back a couple of the sensors from the previous test stand, being the strain gauge for thrust and torque, and then also the optical sensor for RPM. But in addition, we're adding 2 new sensors, accelerometer for vibration sensing, just as a safety measure, and then also a voltage and current sensor for motor power monitoring. All these sensors work and operate, communicate in a little bit of a different way. So in these next few slides, we're just going to break down each of these components and how they connect with the system, starting with the strain gauge. So we're going to stick with the same amount of strain gauges, 3 as the previous test stand, 1 for thrust, 2 for torque. The only difference from the previous test stand to this, to our current new stand, is that we're going to be using what's called an HX711 amplifier board. So all that's going to do is it's going to be able to take in the voltage potential coming from the load cell and translating that to a data and clock line coming out. The really nice thing about the HX711 is that it's small, it's reliable, it's readily available, and there's a lot of resources online. So if we ever need to integrate different sensors, we can do that. In addition, it also accepts a wide range of load cells. So if we wanted to implement a 1 kilogram or 20 kilogram load cell, we could do pretty easily. If we needed to swap those in and out just to look at different accuracies, we'd have that capability. And that sort of aligns with our ability for keeping the whole system modular. Again, swapping in load cells, or even if the amplifier boards would go down, we'd still be able to swap those in and out without having to change much else in the system. And then finally, the HX711 will also be able to communicate with the ESP32 board just through data and clock into 2 GPIO pins. The only difference that this graphic is showing as compared to what our system is going to do is this one's showing that it's powered off the board, where in reality, we're going to be powering it off of a separate power supply. Again, that'll just be able to work that way. So that's the first sensor that we're bringing back. The other sensor is going to be the optical one, and Thomas is going to talk a little bit about that.
So we are bringing back the same optical sensor that's used in the previous model to record RPM, same objective. But we're going to kind of change it a little bit. The current model is pointed at the motor, and it counts every time a reflective piece of tape comes around the motor, and that's how it does its count for RPM. That won't necessarily work for our new design because they want to use 3 different interchangeable motors and of all different sizes, so that we calibrate differently. So we're going to do it by pointing at the propeller. And so we've programmed it so that it will count every time the propeller passes by, and the ESP32 is programmed to divide by the number of propellers that's inputted by the user. So by doing the 2 of that, the signal is sent from the IR sensor to the ESP every time it receives a positive, which is just something in front of it, and that will cause it to count up, and then it'll divide that by the propeller or the number of blades, and then the time that it takes to do so. Another sensor that the first sensor that we're adding is the accelerometer. By adding the accelerometer, it's more of just a safety feature. So it's going to detect how many, I believe it works in G's, however many G's it detects, it will send back to the ESP. If it records too high of a value, it will tell the ESP to shut down the motor. A big issue with the current stand is that when it does vibrate too much, everything starts shaking and it needs to be shut down because it will destroy either the board or the propellers that are attached. And once it gets dangerous, things start flying in the wind tunnel. And to show how that power is shut down, Kevin's going to go into our power measure.
Yeah, so the last detail on sensors here has to do with measuring power of the motor. And to calculate power, you need to measure current and voltage. So we have a sensor for each of those. You can also see how they're hooked up. Voltage is measured in parallel, while current is in line with the negative rail of the battery. Those are both fed into the ESC, and then the ESC turns into a 3-phase power for the motor. You can also notice that there's an emergency stop on the negative rail of the battery. And there's also a PWM signal coming from the ESP32. But let's get further into the current and voltage sensor. So the voltage sensor is really just a voltage divider, whose output is going to be R1 over R1 plus R2, right? So we bought this board already and have prototyped with it. And we get, it's somewhat accurate data, but there's still an offset, a voltage offset that we haven't been able to figure out. So we took it upon ourselves to just make our own voltage divider with resistors we had on hand. And we're actually able to get a fairly reliable signal from 0 to 15 volts, which is the operating range of the motors that we're going to use. So that is something we're looking to build ourselves. The connection to the ESP32 would be the same. We just we would have a VCC, a ground, and then one analog GPIO pin. And then the current sensor is very similar. So we looked at a few different kinds of these. There's different kinds. One of them being the Hall effect current sensor, which takes a magnetic field and then turns that into a voltage, and then you can deduce current from that. Another one, which is like the one we got, which we purchased for prototyping purposes, uses a shunt resistor, and it measures the voltage across the shunt resistor, and then you deduce current from that. Like I said, the terminals are in line on the positive end of the battery or power supply, and then it's just gonna have a VCC, ground, and then one analog GPIO pin to the ESP32. So the last detail here is where's the power coming from, and we have two power systems we're dealing with. One of which is going to be for the embedded system. So this is going to be our 5-volt rail, 5-volt and ground. That's going to power all of our sensors, buttons in the ESP32. The second one is, as of right now, going to be just the LiPo battery. These are readily used for like quadcopters and drones, and this is what typically teams who would be using the test stand would have on hand. An option that we've talked about, but it's not confirmed yet, is to use a power supply for the motor itself, so you wouldn't have to charge batteries. So that's still to be discussed with other teams. We're kind of waiting on some information. So for right now, we're just planning on using batteries. And if we do want to use a power supply, it would be as easy as just switching out the leads from the battery. So they make all different sizes. You know, another option that we talked about, again, but we're waiting, is like a battery bank for like these. So like rather than using a power supply itself, you can just like put some batteries in series, and then you wouldn't have to charge those as often, you know, like. But again, we're waiting for some information from Dr. Jimmy on this. So
Don't put batteries in series, but they're parallel. Okay.
so yeah, with that, I will turn it over to Connor.
Thank you, Kevin. So for the last subsystem, we have the control system. And with the control system, the main controls of the system will be controlling the RPM through a PWM signal, as well as having a start and stop function. Now, we don't have the entire specifics of what those start and stop functions are going to involve in its entirety. We do have a good idea on how it's going to function. So once you initiate the system by starting the start function, you'll be able to select a targeted RPM. With that targeted RPM, that will then be translated into a PWM signal that will be sent to the ESC, or the electronic speed controller. Once that is sent to the ESC will control the current and voltage accordingly to make that motor spin at the correct speed. From that, once it reaches that targeted speed, two options could occur. One is that the user alters the targeted RPM once it's reached it, either through the physical controls or through the PC interface, both of which we'll be going over in the next slide, which will update the PWM signal going to the ESC and update the motor's RPM accordingly. The other possibility is for the user to initiate the stop function, which when you initialize the stop function, it will slowly ramp down the motor in a safe way, as well as stopping all recording that's currently in process. And so you might be asking yourself, like, this sounds all great, but how does the user control it? And so with that, the user will be able to adjust these settings of the propeller test stand through a PC interface as well as a physical control panel. On the physical control panel, which is represented by the components on the right, will consist of a start and stop button, a rotary encoder with a switch included in it, as well as an emergency stop. The start and stop buttons function basically as initializing the start and stop functions represented in the previous slide. And the emergency stop cuts all power to the motor in the event that something is going wrong and things need to stop immediately. The rotary encoder, which will be connected to the ESP32 via 3 GPIO pins, 1 for the switch and 2 for the rotary encoder itself, as well as power and ground, will act as a way to physically change the RPM. It'll start off at whatever the targeted RPM is, and it can go up and down at set values. By clicking in the rotary encoder, you can turn on an acceleration mode, which will allow you to change the RPM at a much faster rate compared to its step-by-step intervals. For the physical controls, we limited it to just the main controls, as we believe that these are all the controls you may need while working with the rotary encoder while working with the propeller stand while it is currently on. For anything more advanced than the basic functions, that would be done with the PC interface. And the PC interface will be able to do all the physical controls with many other additional features. 2 notable ones that we plan on integrating include setting the target RPM instead of it having be a default, as well as setting a time to ramp up from 1 RPM to another RPM so that you can see how that ramp up and how that speed changes everything. With that being said, with all those subsystems being explained, they all sound great and separated, but they won't work if they're not tied together well. In order to tie them together well, we need to develop a good software. So with the software, we have 4 main goals. We need to be able to establish the connections to all the components. We must be able to send and receive data to the ESP32 very quickly to ensure that we're logging data at a sufficient rate. We need to be able to calibrate all of the sensors so that the data we're getting is accurate. And we need to be able to show the data as well as show the calibration settings through that PC application. We are doing this through the Arduino Integrated Development Environment, or IDE, as it'll allow us to use libraries to assist us in developing the sensors further at a much quicker pace, which even then has been taking us a longer time. With that being said, so far we have started the software development so far, and we've been able to establish connection to almost all the sensors, excluding the current sensor, and as well as the rotary encoder. We even today have 2 demonstrations showing how the rotary encoder can be used, as well as how the strain gauges send and receive data from the ESP32. We also have been able to, with the strain gauges, export that information into an Excel file that can be viewed at a later point. And we'd like to show you those demonstrations at the conclusion of this presentation. But as I just mentioned earlier, the software development is taking the team a lot longer than we originally expected. And we believe going forward that it is still going to take a large chunk of time. And due to that, we took into account the progress that we've made so far and have planned the spring semester accordingly, as Kevin will now go over.
And so this is the autumn semester schedule that we showed for our PDR. We've made a lot of progress. We had some lofty goals. We've realized now at the end of the semester that we still have a couple more things to do. While we did get to the schematic development, started a prototype, started to do software, we didn't really get to a troubleshooting phase. We're still really getting into software. It is taking a little bit longer, I think, just because it's not, what we're most proficient in. But looking at next semester, we've accounted for that slight delay. So we're kind of in an okay position here because we were able to purchase parts last semester. That really, really helped out. If we had not done that, we'd be even further behind on some of the software stuff. So that was like a huge, a really good strategy for last semester. we weren't able to finalize the bill of materials, but we think given like 3 to 4 weeks at the beginning of next semester, let us flush out sensors and controls, figure out the power system stuff, mainly the current voltage sensors. That early February, we're going to be in a really good place to submit our final BOM and order parts. During that time, we're then kind of breaking the semester up into 2 phases, a preliminary build and a final build. The preliminary build is going to be, there is the physical build of the thing, but what we're realizing is that's going to be a lot of software development time. But we want to get to a point where we can submit a test plan draft by about mid-semester, and kind of present our preliminary build. At that point, we'll go through, revise our design based on sponsor feedback, other teams' feedback, your feedback, and then go into our final build phase. We've got about a month slated for that. And we want to finish early April. So we have time to like validate our designs, and that's just to test our sensors to prove that they work and are calibrated correctly. So that's our plan for, I guess, how we're going to go about the technical task of building it. As far as more administrative things, we really want to include all teams meetings next semester and have those like scheduled first week, where everybody aware of when the dates are, where it's going to be and what we're going to talk about. So we've got one at the very beginning of the semester, one in the middle, and then one a couple weeks, or 3 weeks before the end of the semester. So we're really hoping that planning these early is going to allow everybody to figure out their schedule and meet, and we're not going to have to suffer the difficulties we've had this semester with communication. So this is kind of our, it is all preliminary right now. Obviously the stuff will change. We plan to be flexible and work around those changes. But I think this is a really good basis to start off with for next semester. So going a bit further with project management, we also have developed our cost estimation a little bit further. So previously we ordered less than $100 worth of materials for prototyping. And that was, again, crucial in moving the project along. Now we're realizing, okay, we've got all these components talking to each other, interacting. Well, you can really choose any one of the components and, increase the quality of that product. For example, the buttons, right? Is this something that kids untrained in the AeroLab are going to be mashing? Do we want something that's super durable, that's going to last for years? Something to consider. Same with the rotary encoder, the e-stop, selector switches, the enclosure itself, cables going into the test stand from the enclosure, and power supplies. So we're estimating around $1,300 for this right now. Now, again, this is an estimate, and it's still well below our $2,000 budget. So
$2,000 budget.
so the $1,300 plus our $100 for the prototyping goods still leaves us, $500 for things that we're not accounting for, which, as we all know, things come up and realize, oh, gotta buy this plug or these terminals or stuff like that. So leaving ourselves a little bit of wiggle room there. And so yeah, that kind of wraps up our design portion of the presentation and project management. And we'd like to turn it over to Michael to talk about some of the challenges and lessons learned.
So there were 2 major challenges that we encountered this semester. The first major one was software, whether it was Arduino or design software. We ran into quite a few challenges there because based on previous experience, a lot of us didn't really have a ton of software experience. So when we were looking at Arduino, it was really crucial for us to figure out how to get all the code for the sensors integrated and actually working. And then once we got the code for the sensors, sort of bringing it together and making sure it worked in harmony. In terms of the design software itself, again, not a lot of experience around here, but when looking at the schematic, like the circuit schematic, and we just really needed to learn how to do that first. And then eventually, if we want to try to implement a PCB somewhere in our design, learning KeyCAD and stuff like that, being able to translate from that one schematic to a PCB schematic is pretty crucial. So one of the best ways we were able to tackle that this semester, and especially going into the next semester, is sort of looking at our resources, what's available to us, how do we figure this out. So first looking at ourselves and looking at as a team online resources, for tutorials, guides, videos, just how to learn this software better, learn how to code it better. And if we can't do that, then turning to in-class resources. We had Jonah and Zach, I think, who were the two TAs who were just really well-versed in these types of software, whether it's Arduino or just design. So really utilizing those resources because they're there, they're at our disposal, we might as well. The other major challenge that we faced this semester was just communication and collaboration with external teams, more specifically the aero team and the mechanical team. Now, whenever you work in a capstone project with multiple teams, it's really hard to get on the same page because everyone has different schedules, different timelines, especially with different classes and stuff like that. It's really hard to communicate that effectively. At the same time, when it comes to bringing ideas and sort of thinking about how to integrate the system together, that can prove some challenges as well because everyone's going to have different ideas. And then finally, just communicating responsibilities. I think we noticed in this project that there was some gray area in terms of who was supposed to do what, but being able to just like work with the other teams, communicate that and collaborate, those issues can be solved pretty easily. So going forward, we definitely want to try to introduce a culture of that communication, of that collaboration, so that especially when going into like testing and actually building this test stand this next semester, we're on the same page, we'll be able to communicate effectively, like Kevin said, making sure that we lay the groundwork early and set these major milestones in terms of these meetings that we're going to have to make sure everyone's sort of on the same page and moving towards a final product. So through these challenges and just the rest of the semester, there's quite a few lessons learned. And the first one is communications. So again, whether it's internal or external, making sure that we have a dedicated communication source, which was for us, it was Microsoft Teams or email. That's like super important, but mainly that's to organize meetings, which those meetings you got to be careful with because you don't want to just hold as many as possible. You need to make sure that they're structured properly, whether you're having work meetings or progress meetings, that needs to be communicated effectively. And when they're actually in session, they need to move along because at the end of the day, everyone, including our team and other teams, everyone has different things on their schedule. So time management is pretty critical. I think Connor mentioned it, or he said it best, where capstone is sort of like an internship, where it's like, we basically have all this work that we need to do. And typically in past internships, we've never had school at the same time. So being able to figure out how to manage an internship while having a full course of class or full schedule of classes is super challenging. But that's definitely something that we've improved a lot on this semester. And I think as we go into the next semester, we'll be able to do that as well. So in terms of the actual project itself, there were definitely times where when looking at, coming up with the idea, coming up with this system, that we really wanted to dive into stuff. But then there was also times where we sort of had to step back, sort of look at it as a whole and understand where to go next. But we found that really diving in and prototyping, like Kevin said, getting those products or getting those components early, we really were able to figure out a lot of the situations and problems that we encountered, especially with software. So that really helped us improve our design. And then sort of we were able to go back, prototype, improve, and sort of do that process all throughout. But at the same time, especially earlier on, when just, coming up with the project itself, everyone had great ideas coming back and forth, but a lot of them ended up being features. And we really wanted to look at the system as a whole. So we sort of had to step back and say, okay, what are we trying to accomplish? And at the end of the day, functionality was the key. Once we were able to figure out functionality, we could then dive into features and actually develop a system that we were really proud of.
So to summarize, we're on the right track. We've found things that we need to work on. We need to work faster than we were before, which we have planned into our next semester. We've sort of found a way that we can consistently communicate with the other capstone teams. That was really probably our biggest limiting factor, being that we just couldn't talk to each other. And talk to entire teams at a time, maybe one person that didn't know it. We've got most of our sensors communicating with ESP, and we just need to dial in the rest of the Arduino code. And if you'd like to come up here, we can show you some demonstrations.
Yeah, well, thank you for the presentation. I'm gonna pause this. This is the demonstration part.
Yeah. So we'll show you the strain gauge first.
Team strain gauge, come here.
Yeah, so again, strain gauge amplifier board, really easy connections. nothing too
Kevin,
crazy.
I do not expect this from you,
You know,
right?
Mhm.
You know, and you didn't do it, just
Mhm.
like 2 pins.
Oh, yeah,
Right?
yeah, we just had to like move a lot of stuff, so.
Well, yes,
I
exactly, for
know.
that reason, this has to be like there. Same
Secure,
as this
secure,
guy,
everything.
right? Because you don't want unwanted shorts.
Right.
Okay, let's do this. Do I press on this guy?
Yeah, so you'll be able to see,
So tell me, what am I seeing?
right, so this is
Because
just
this is
a,
not being pressed, but it has negative numbers. Do
yeah, so.
you Calibrate.
Yeah, so this, the sensors still need to be calibrated. That's, because I haven't been able to design and build like a calibration stand yet, I haven't been able to calibrate it
Tell me
properly.
how you want to calibrate it.
How we calibrate, so there's code already, that you can literally just calibrate it there, through the libraries that this HX711 amplifier board has. You can calibrate the
I
load
know,
cell.
but this is an analog thing.
Right,
right?
okay, so you
So-
need to use a known weight.
Yeah.
And
okay.
basically through that, there's like it's basically a calibration factor you get from that. And then you apply that to whatever measurement reading you're getting, and then based
So
on,
why did, where there's why there's a negative number? Is it like inverse?
it's just not calibrated properly right now.
Oh, okay.
But the idea behind this, or at least what we're trying to show, is that if you flex the load cell, it'll change. So it does show that it's changing, so
Huh.
either way you flex it.
So interesting.
Yeah, and the nice thing about this is, so it's actually running right now in a putty
Who's
SS.
stronger?
Hey, don't break our stand gauge there.
Yeah, we could actually end up breaking it. I mean, you gotta be careful.
All right.
But this is running right now in a putty SSH client. So the reason we're doing that is through this, you can actually log to CSV files.
Can you
So-
then plot it?
Yep,
Mhm.
yep,
can
exactly.
plug what
So
I'm doing.
right now it's recording to a CSV
Oh,
file.
that's nice.
Yeah, and then if you want to exit out, you can show her.
Someone's
that
been
works.
working hard.
So once you exit that out, you can then go to where the file was saved. And this can be done for, this should be able to be done for all the other values as well. So these are all the values.
So why there are two G1, G2, G3?
So originally, we were trying to show all three strain gauges, because all three strain gauges work the same, like they all work the same
Okay.
way, and we want to be able to show that, but because we don't have a power supply, it was just easier just to
So
show.
the strain gauge, like all three axes, you have it on all three axes for the test stand? Is
Correct.
that the plan?
So one is for thrust and then two are for torque.
So they will be on different devices, but they all be measured at the same time.
Yes.
Yes, yes.
Okay.
Yeah.
So this is your very raw data, right?
Yes,
So like if you want to plot this right now, then you have to one by one pick them,
Mhm.
right?
well,
um,
what do you mean one by one pick them?
Like you have numbers 0, 0. If you just plot all of that, that's not a meaningful.
Well,
Yeah,
yeah, I mean, well, I guess if what you're saying is, so.
Yeah, I just want to see SG1 plot.
Yeah, I mean,
But
the
you
only,
have to
like
know
I
the
said,
manual.
the only reason I have SG1 only here, I mean, I can adjust the code a little bit just to show SG1 only.
No, even if you
I
have all
think I see
three
what
of
you're
them.
saying, though, the format of the CSV
So,
file.
yeah,
Oh,
if
Would
you
be
have
that
all
it's
three-
very.
So instead of having
Yeah,
them in
okay, I see,
row,
I see.
have them in column.
Yeah, okay,
So you have timestamp.
Yeah.
SG1 times, same timestamp
Yeah.
as SG2, SG3, and then for plotting, you can just grab that column and plot it.
yeah.
That's
no,
what I
for sure,
meant.
Yeah,
For sure,
CSV
I get it.
This way, you have to like literally take every single one
Yeah,
or remove all the zeros, you know?
Yeah,
In
Yeah.
that way, like even if one of these blew up and you don't care, one column would be like.
and we should be thinking about this for all of our other sensor data.
yeah, no,
too,
for
how
sure,
we should- how
for
we
sure,
can
just
format it.
formatting the data, yeah.
Take note of these because these are the things like everything you do, if you don't think about this little thing that's end user part,
Mhm.
they're like, oh, what did they do? This is not even working.
Mhm.
This is
Yeah,
not convenient because at the end, they only see that output. So user is really important. You have to put yourself in their shoes. Now, one good way is like, for example, I'm looking at it, I'm like simply from user standpoint.
Yeah,
I want to plot this and I wanted to see how, like, when did I deflect it?
yeah.
Because I
yeah,
also
yeah.
pressed on it and I also deflected. I
Right.
wanted to see how that could be. If this was in a column, you
Right,
could just
no, for sure.
right
Right.
away
Yeah.
plot it and show me, right?
And,
Right,
and
yeah.
that's what we'll have to work
Cool.
on for sure.
All right,
sure
show
you're
me
able to
this
do that.
guy. So this has the amplifier.
Oh,
So without the amplifier, were the numbers so close that you would not recognize? the
So
difference?
the whole point of the amplifier is just, you can't plug these wires directly into the ESP32 because this is just measuring like voltage potential. So the ESP32 doesn't have
understand that.
it doesn't have the capability of reading
Oh,
like,
this is the amplifier.
correct.
This is the driver, what is
That's
it?
usually accelerometer.
Oh, that's the accelerometer.
Oh.
Yeah, we weren't,
Take it off.
yeah, we just didn't take it off.
Well, that's a better implementation than this guy.
Yeah, well, it had the pins already. So,
Giving you a hard time.
I know.
That's why when you go and read my professor, they say she likes to grill her students.
That's why you have a
She likes to roast her student. I don't know if you've seen it or not.
So,
I'm like, you see that, you should take a class with me, so you should wait for being
Yeah.
roasted.
so fortunately, the only thing we have not been able to fix with this is there's it's supposed to prompt you to enter a value between 0 and 20,000. So what value would you like to enter between?
What that value means.
That is just that's just a standard range that I just.
I know, what does it mean? I don't know, like
That's
this,
the desired.
this is potentiometer,
Yeah,
that's the RPM.
so this would be the RPM. value.
Okay, so you need to fix that. Please enter a value between this and this, which map to RPM from this to this. Because I don't know, like, that's one of my questions. These are not one-to-one mapping. It is really important. This is the part of when I say meaningful,
Mhm.
because what works in the code is very different from what you interface with the user, right? So now from the RPM standpoint, what does 20,000 mean? Or is it just a number for now?
Right now, it's just a number.
It will be a
It will
number
be.
that you're mapping, right?
Yeah.
Mhm.
A
We'll
RPM between what to what?
believe, what was our ideal range? 0 to
25,000.
25,000.
25,000, yeah.
And then it will map to some number, which will be voltage, right?
Yes.
So let's say 1872.
The other thing I'm just thinking about right now with this is,
So this means the starting value at that number, okay, that's, so
So the current,
that's our desired value.
so this is the value that you started. So yeah,
Yeah,
this would
it's
be the
currently out
desired,
here. I'll
like
hold it
RPM
so you
value.
get the full experience of.
I can do that.
Oh,
I can't complete your.
Just so you can see too, because I want you to look up there.
I know, but I don't understand the 185. Let me change.
So that's the
it.
number, that's our set RPM, right? So now you're changing the RPM. This is what we're gonna send out to the motor ESC.
So you have steps.
So that's like a set, so it's almost like a feedback
50.
control type thing,
It's
right?
not, actually, it's not feedback. I
One,
put it
there's
there.
not feed. it's not
There is, the feedback is missing.
So
I
it's-
wrote it there.
So it currently goes 50 per step, but if, as I mentioned in the presentation, if you want to go up at a faster speed, you can click in the stem.
They change the sensitivity.
There you go. So now acceleration is enabled. So now if you spin faster, it'll go up at a much faster rate.
What is the rate? What's the jump?
That I'm still trying to figure out because
50.
the library that we're using just says to use.
No,
the
it's still
value.
50. Look at the.
So if you still go slowly, it'll still go by 50, but if you start to go
Oh.
fast, it'll.
So there's a
jump.
rate.
Yeah.
So here's the thing, that's exactly my comment. I'm glad that you did this, so we can have that conversation. So these are all great that you figured out. Because like you can see that I have that comment. So this is a tactile thing, right?
Mhm.
So I'm moving this, I have no sense of what is happening. My way of knowing something is happening is look at the problem or is going crazy fast or slow, right?
Right.
So how are you gonna connect these two for the user, for the interface? Because your project is for a user, like everything you're designing has to be user aligned, so the need to be user friendly and basically useful. It's really, really important. It has to impact all of your design choices. How do you fix this interface problem that I have right now? From the first question I asked until now that, okay, I'm going as fast, we haven't figured out yet. I disabled it, and then even now, I'm in fact going fast, I still that, but then I enable it. How fast should I go to get to the thing I want? Because when they test, they have numbers. that they
Right,
have to follow. How do you fix this?
Mhm.
okay. Not entirely sure how to.
Okay,
yet, but then-
that's a very good question to think about. Now, this is analog, right? That's the problem we have with analog. You have steps, you're limited to the number of steps, like basically the rotation.
Yeah,
So one way is to make it smaller steps, right? Which you have to see physically what is the capability of this potentiometer. You might find a better potentiometer with higher resolution, right? And then leaving that rate to the user is usually not a good idea. One thing you could do could be, I don't know, I'm just thinking, if I could see on a monitor, like on a LED screen, the number I said, but it doesn't act until I said number is good. Now do it. So I can play until
Good
I'm
idea.
around the number I want,
okay,
right?
yeah.
And then I say,
Mhm.
this number looks good now, do it. So it's like a reserve like cache kind of thing, right?
Yeah,
So I was like, oh, this number looks good now, press something, then run it. So
okay,
they can play with and then not be penalized for going too fast or too slow, breaking
Right.
something, if someone doesn't know. There's an approval from the user. Could be clicking on a button on the interface, or could be a button here that execute,
Mhm.
right? Then
Mhm.
you'll be fine. If this doesn't have the resolution, you'll say that this device's resolution is this many steps, which is RPM. It could be every 1 RPM or every 2 RPM. They have to adjust their test. They can interpolate, extrapolate, find out the data, right?
right,
So if choosing a different sensor helps you to improve the resolution, you should do that.
okay,
If you're limited, then you will write the instruction for them.
Mhm.
If you couldn't fix it in the mapping, because this is basically voltage reading, right?
Yeah,
And then
essentially.
translate into a number that the motor will spin, which is the RPM, like the PWM. You will have some limitation on PWM as well.
right,
So you need to find out these limitations, and it will go to your instruction manual. When they run the code or they see the interface, it will be right there that this is how you use it. You only can see this resolution, and then you have to approve. And then it will be fine,
okay,
Mhm.
right?
Mhm.
Yeah.
Does that make sense? Now, the part with the feedback control. So you had really nicely feedback from the user that if the user wants to change the RPM, right? So they should be able to, so I know that they can stop it and then it slowly will turn off, which is great. It doesn't change abruptly. Now, what if they want to go to a different RPM? And then when they spin this, would it abruptly go to the other one? Or would you, like, what is the plan? I don't know. I'm
So
just
I
asking what the
think
user
sir.
want. I don't know. I'm not
Right.
asking what you think. Did you ask the user what they want?
so no, that was gonna be one of the questions that I had for Dr. Deborah
Write
today.
those
Mhm.
questions.
Yeah, we have it written down.
You have it? Okay, you have it, okay. Because again, this will change the way you code,
Mhm.
right?
Okay.
And this is what you have to ask Dr. Jemmy, not the other teams,
Mhm.
right? Because
Right.
he decides. And then these are one of those minutes of meeting that needs to be approved,
Mhm.
because that will basically impact all the coding you do and all
Right.
the design, the PWM and everything,
Mhm.
right?
Yeah.
So that's one thing. The second thing, let's say you say, okay, I want to go to 2,500 RPM number, which correlates. So what I see here should be RPM on the screen, right? Doesn't matter
Right.
how it rotates. And I see 2,500. In your control loop, there's no sensor checking if the motor is actually rotating 2,500. It's a one-way, it's an open loop. So if the motors they choose have encoded better, have encoded, you're gonna read that number back to make sure it is 2,500. If not, it has to keep feeding. So this won't change, but your PWM has to change until the motor encoder says it is 2,500.
Okay,
Mhm.
Right?
Yeah.
Because the user can, this is desired value from the user input,
Mhm.
right?
Mhm.
What happens in your system is your control loop doesn't have to do anything with them.
okay,
Then you can't tell them now, like rotate 1 more degree. You know, it was 2,500, just for any loss or anything, it's 2,485. There's error, right?
Mhm.
So you have to make sure the encoder keeps sending back the error until the PWM has to increase until it reaches. That's the feedback that you need.
Okay.
all right?
The
So,
other thing,
yeah.
just thinking about now is just like setting the RPM too. I think we might run into issues because like you're limited by the motor, each individual motor's capacity. So if the motor can't even reach 20,000, you set it to 20,000, it's just gonna go up to a value.
So I want you to go
It's
back
not
to your requirement table. This is a good point because it reminded me of another comment I have. Can you go to your, so great job on this. So this will also be a CSV file. What is the output of this? This just spins the
So,
motor and you can see the RPM being plotted, right?
yeah, we can plot to a CV.
It can be plotted.
CSV file,
Okay.
or if it's only needed for internal use, it can just be.
Okay.
Internal.
So what's the point of this test for that? Like, okay, rotate to this RPM and then they're measuring vibration and everything else?
They're measuring
not?
torque and thrust, is
Oh,
what
okay.
they really want.
So you just want to make
Yeah,
sure you
they
have the
really want
correct.
Correct.
So if they like tested it like 5,000,
Yeah,
like
yeah,
10,000
sure.
units.
Makes
They wanna
sense,
see
makes
the
sense.
commanded
Yeah.
value.
Now go to your requirement table. So one thing that you mentioned is the capability of the motor, right? So where is that? Where do we have speed? So if your requirement is 25,000, when they're speccing the motor, this is really important for them.
Yeah.
Mhm.
To the minimum, the nominal value should be probably more than 2,500.
Yeah.
So they have to spec based on this range, because usually nominal value is not what you actually see.
Mhm.
Okay, so basically you have to go back to the motor selection, make sure that one is checked. Then the torque also must be provided, so it has, so basically your end range is where you'll be safe to provide the ideal. Did that ideal number came from Dr. Jimmy?
Yes,
Mhm.
the ideal numbers came from. the
Okay,
emergency
so they
department.
need to be able to measure thrust by 30 Newton, torque of 20 Newton, 0 to 20, right? And then your motor control, why is that in a requirement table?
It was, we have it there, it's just a way that there needs to be a physical way to control the motor.
Because this is, you're trying to imply the controller, but you're using PWM, so start, stop, ramp. Is that the control input signal?
Yeah. I think
So
that-
they
that
should
would
be
be
able to
better.
ramp up. Is it like a step and ramp? Signal generation?
Not entirely sure yet.
So
exactly.
that, instead of motor control, has to be input signal type, right? That means that you should be able to, so start and stop means what? Providing 5 volt, providing 0 volt, that's a step.
Mhm.
So step input, ramp is go from one number to the other, right? So these are your input signals that the system needs to be able to receive. All right, change that.
Mhm.
Power, where did you get that? I don't know if you discussed this or not, but it grabbed my attention because it will go to the motor selection. So why is there power there, first of all?
Jimmy specifically said he wanted a motor that was 500 watts
Or less.
or less.
So what I understood is power consumption of the system is 500 watts.
Mm.
So your power consumption, so that has to be motor power.
Motor
Right?
power, yeah,
Motor
yeah, not
power
that, yeah,
is,
yeah, yeah.
Because, so I would probably, like, I think that's what you kind of did. I would still break it in 2 parts, clearly write requirement for motor selection. Like a header, like you can do, you know, this and then, I don't know, this. So like merge all of this motor selection, which is thrust, torque, speed, power, motor power, right? And then motor's input signal. Those are all like required for the motor as input to the system as a requirement. Which you're not choosing it, the aero team is choosing it, you're just checking.
Mhm.
You basically make sure the right one was chosen. Okay, and then your requirements are the ones down there. So logging frequency, right, which you pick your microprocessor MCU based on that, it's fast enough that it can log it is one of my questions. Are you still good with like 50 as ideal, 50 hertz?
Yeah,
So
yeah.
make sure that the resolution of all the sensor you're choosing matches that.
Right.
Yeah.
And then user friendliness, that all the things that I just talked about, all is user friendliness. Physical RPM control, what's that? Isn't that this?
Yeah.
Yeah, that goes hand in hand with the.
So that's the
control
ramp
motor.
thing, right?
Yeah.
Mhm.
So you don't need it?
Uh,
Because you said
yeah.
taper 1 to 100%, means that it has to be able to do like a ramp.
My thinking was it would be able to go from zero, like if the starting value is 0, it should be able to go from 0 to whatever the 100% capability of the motor selected is. So whether that be the,
How does this impact your work? So my question, how is it your requirement? How would it change anything on your coding?
honestly, the only thing it would change is probably the max limit on the
If
code.
someone else chooses the motor,
Yeah,
right? You just have to be able to read it, so it's kind of,
But
I think-
isn't it still part of our requirement because we could write the code so it wouldn't go all the way up to 100%. We want to write the code so that it would go from 0 to the full max value.
because
even
when you
if-
say
even if-
physical RPM control is this guy,
Mhm.
physical device, right?
Mhm.
Um,
I guess that uses the code, so it's sort of.
so I'm trying to word it better,
okay,
so it's. Paper is not a unit,
Mhm.
right? So it's a made up word. It explains that though, right? So I'm trying to see if we can define that. So that is ramp going from 0 to max capacity of the motor, correct?
yeah,
Okay. So like ramp signal resolution or limits. That is also, I think, like, you just need to ensure that you can read that the higher speed, right? Which is your logging frequency.
Yeah.
So you're able to read that frequency, then you'll be fine. But yes, you can, I would think changing that just technicality, PC communication, great, vibration sensing. So this is the acceleration, right?
Yeah.
So one question I wrote is, so your accelerometer is not advertised as vibration, you're just using it.
Mhm.
Why didn't you use a vibration sensor? We have in the lab. Test it. We have vibration sensor is in the lab. I would say test instead of accelerometer. It might be better.
Okay.
You might have all
The
this. Like,
difference between a vibration sensor and accelerometer.
I think it might have the driver or the code that tells you about the vibration, all 3 axes.
Okay.
I'm not sure, I know that also works based on acceleration, but I know we have vibration sensor spec and advertised as vibration sensor
Mhm.
and accelerometer.
Yeah.
The accelerometer might not be sensitive to all changes of acceleration. It might be like a filter inside, like every this many sample, just read one acceleration.
Mhm.
Vibration sensors for higher frequency,
See.
okay,
right? So there's a difference. I think the vibration sensor, I think is in that blue box. Well, I would change things around.
Mhm.
Next semester, ask me about vibration sensor. It's in the lab, you can take it. Don't scrape off this guy, test the other one as well,
Sure,
Mhm.
sure.
right? Might actually look kind of the same as this one, but just an idea, so you're actually using a vibration sensor.
Mhm.
You said that, let's see, if I go, I think you were. So you said you never hike. You brought me the mask.
So
Yes. So you said that you're troubleshooting your design. You couldn't finish troubleshooting your design. You're not at this stage of troubleshooting. Troubleshooting happens at the end of second semester. You're in redesign. You're actually doing the troubleshooting you meant. You have changed so many things since last time I've seen your project. So, again, terminology. You have to, like, if you said to someone, you haven't done troubleshooting, you're like, oh, is your project done?
Yeah.
Yeah.
It's
You're
like
just in the prototyping stage. Prototyping means this doesn't work, scrap it or add something to it.
okay,
So I would change the wording. If you're presenting this to someone else, change it.
Mhm.
For me, it's fine. I understand what you mean. If it goes to your report anywhere, change it.
Mhm.
Yeah. Can I brag to these people? What you do?
One, two.
Oh, you didn't bring the mask.
I have a mess with me.
It's okay. I'm gonna show them. So then we do mask.
Wow, that's awesome.
that's cool.
So you put it on the mask. You put it on the mask and then it basically monitors your lip motion. And then, yeah, so, well, there are a lot of situations that you need to actually hear. And, the plan was for them to have the, microphone also, so you could actually hear. And it's speech to text transmission, but they like, didn't get. So they changed the scope of the project, which is something that is always expected in engineering projects. So if you also had to do that, it's totally fine. Yeah. So this has to just be on your lower lip. It will go
Do you mind if I
here,
take a video?
and then
of
when
this?
I talk, it should change. Is this correct?
The sensor.
It just
oh,
has to, the sensor
yeah,
has to be on my lip.
I saw it moving.
You saw it moving?
Yeah, it's moving.
It is moving,
It
like,
is.
so I'm like from next generation. I'm from future. Yeah. So, really great project. It was very difficult, but, changing the scope, finally they have product and I can show you. Can I open this box?
Yeah, it's just taped up, so you should.
Untape it. So that's why I want you guys to do PCB. Look at that. They design everything. This is the ESP32.
Wow.
They for the chip. There's so many things that went wrong, but they were able to. This is your third or second
yeah.
iteration that they printed, but since they were on top of it, they order everything so they could go through 2 PCB. So we ordered this like last minute. They have everything. They had everything.
No,
I broke this one. This is
no,
very.
yeah, that just slides on especially.
And then the little one also has a PCB.
Yes. It's
That was very
tiny.
impressive.
Not that many components on it. It
But
just has
very
a-
impressive.
There's a mic on it.
Yeah,
It
I'm
has
not
a
gonna
sensor.
open that.
It's,
So there is a
I don't think you
PCB.
should open it. It's
Okay.
hot glue
they
shut.
have glue shut. So with the microphone, so you can see that. This is the motion sensor. This is the microphone.
So it's like measuring sound, is that how it knows
Oh,
your
no, it's
thought?
measuring movement of your leg.
So, and the plan was to also like decode the sound and look for the syllabus or phoneme and say like, oh, the lip should look like this because it's not
Oh,
always
yeah.
open and closed,
Mhm.
right? It's like O is different from A. But it was just too much work, so we changed the scope. Yeah. So like right now, if you think about the state machine has 2 states, right? Like state open and closed. So a very good project. They knew I think the best thing they did was the communication and like, oh, we need to change the scope. Oh, we need to change the scope. And I think this is a great product.
Yeah, that's great.
Like if you talk to someone, hey, we need a second phase, we need to be doing this and that, they say, oh, okay, it's possible. Like, you know.
Curious, what were your biggest challenges like with the PCB design, development, all that?
Well, there, you can probably see it, the components are very, very small, but I just trying to shrink everything down. And then the first time we designed it, we made it kind of pretty stupid mistake where we connected the transmit of the ESP32 to the transmit of the USB UART chip. So if you can't,
Connect RX to RX,
Yeah.
TX to TX.
yeah,
See,
yeah.
Do you guys have previous PCB design experience?
One of the
Yeah.
members had it.
Yeah.
But you can get to this if you follow the module and utilize like the TA's expertise, you'll be able to, you like, so that's why I was like a little bit shocked on the price, but you can also ask the manufacturer GLC PCB to do the soldering for you if you don't have, because that is experience like very small component.
Mhm.
So it's a bit more
Yeah, they just use
expensive.
pick and place machines.
Yeah. They're more expensive, but you know that it works,
Mhm.
right?
Yeah.
And the fact how to troubleshoot, how to trace and see everything is connected. So finding RX was connected to RX. That was the biggest challenge and
Yeah.
they figured it out. You know, like, how do you check those? Those are the skills that you need to have. I'm recording all this, was great. So I think like all the experience they have, so next time, like, is RX connected to RX?
Yeah.
Yeah,
Thank
also,
Yeah.
we had another issue with the footprint, so that was a big issue. We didn't find that out till like right before Thanksgiving. So, yeah, the footprint for the spring connector
Oh,
we got it from Mauser, but that one was wrong. The pins on it was somehow labeled incorrectly.
oh,
Yeah.
Yeah, we didn't realize that till
Yeah.
right before Thanksgiving.
So that was also some, like the fact that you can troubleshoot, find the problem, that's a skill. Like where to start, where to look at. So these are the 2 things that now I know if someone's like, have you checked this? Have you checked that? So don't look at it as a scary task. It is something that's rewarding. Because it's all like very tiny, you know, you see like it can go on a face and it doesn't even weigh as much. But it was breadboard, it wouldn't happen.
Yeah.
Or if it was development board, it wouldn't happen. It had to be PCB,
Mhm.
right? So, this is good timing. You get brownie points.
I'm good.
All right, thank you. So, so that's the kind of troubleshooting. This is troubleshooting at the end. Your test plan draft was in March? No, it's gonna be in January. That's one of the assignment.
Okay.
So, the idea is that while you're designing, you wanna think about how am I testing this? And you're gonna write your test. I have a format, like everything you just fill out.
Okay,
And then as you go, it's like, you know what, this is not good. I need to change my test setup. I need to add a few more tests. We update that document. So as you go, you're filling this out. This is your whole assignment for the whole semester.
Mhm.
That and weekly progress report, like you write your progress, you do your test, you do redesign because a test failed and the solution is like, we need to make a change.
Yeah.
That's how you can redesign. So that will change. Communication with other team and even communication within yourself. Are you using Trello or not?
We're not.
So Trello is an online device, especially for teams that they are not in one classroom, different departments. This works out. Look into it. It's an online free tool. You could create like Aero, ECE, mechanical, and put the main task that you want, like it has due time. And you can put due date, you can put a checklist on there. So once they're done, they can check. You can see their progress that is related to you. It's not all of their tasks. So you basically flush out what is it that connects to your performance. And then you have all of yours. It could be all of your detail. They can look into it. It's fine, right? Instead of running to Trello. I think you can even like have like make yours private that you can only access and then have a public that you share that link with them. This way, you can say that, send an email, Air team, Emmy, by February 15, please update all the progress on there. And then if there's a note, they add a note. They need to do that by 15. You don't have to even meet them, right? If there's a comment you put, if you absolutely have to meet them, that will be like 1 or 2 that you put in there. It's a lot easier to go online and spend 5 minutes
Right.
than go on Zoom and talk to people. It's gonna be at least half an hour.
Yeah,
I really
right,
don't
yeah.
have half an hour in my day, but I do have 5 minutes at 12 a.m. And I can update something, like make it an individual thing rather than everybody has to go.
Yeah.
Gotcha.
And for you is also good because you know what Connor is supposed to do, right? And he can check those off. So you know constantly what he's doing. He knows what you're doing. And it shouldn't be that, oh, we divided in 4 different things. Everybody works on their own. We're gonna meet at the end of the semester. No, you see how important it is that you talk constantly to each other, right? So it doesn't have to be just during the class. When using Trello or something like that, you're doing it through the week. Your schedule will be different, but like, I just need to see your progress, or if you came up with a challenge, right? You could create a board called challenges. You could create a board doing, like I have it for my work. Could wait, to do, doing, done, right? Then I just move tasks, I create tasks. I have like check your email every day, and then I create to do, and then empty it. And then just move things, and you like the could wait is like a parking lot. Have ideas, things that doesn't have any major deadline, I would like to do it. And it has improved my work a lot. I already had a check to do the system, but I'm seeing everything right in front of me. Okay, I think your team will benefit from this, especially that you have others. You can even share it with Dr. Jemmy. He can also see, like, it's just observation, right?
Yeah.
He's like supervising. It's like, oh, if you want to check our progress. It's better than Gantt chart because Gantt chart is good, is the big picture.
Yeah, like.
But
Yeah,
like it has February
Yeah,
and
deep.
March and April, like overwhelming. We
Mhm.
just want to know what's happening the next 2 weeks.
Mhm.
That's why this becomes very useful.
Yeah.
I talked about in the class a little bit. So there are different softwares. This is something I use, very friendly and is free for students. So highly recommended for the team. Okay, awesome. I really like the demonstration, so you can see the data, right? You have an understanding. You just need to do the mapping and make those meaningful. Any of these comments, if you can update your CDR, so when I'm reading it, I don't have to make those comments again. So when I'm looking at CVR, I just look over like how it looks. I go to chapter 3 and then see what you talked about if it's there. So on chapter 3, you already submitted, right? No, you haven't, it's
No.
like 50.
Yeah.
So make sure your Gantt chart is updated, so if you have main tasks that needs to be done next semester, but can always be more updated. Yeah. I loved your lesson learned. Yeah, it was good. You'll be amazed how many teams had similar lesson learned. And on top of that is communication.
That was definitely the biggest one.